So here we are, we're back, and we're going to graph f of x equals x to the fourth minus 12x cubed plus 48x squared minus 64x. And we're going to do, this is a good graph. This is a fun one. Okay, let us start with thinking about our intercepts. Let's think about our domain and range, negative infinity, positive infinity, all real numbers. Let's think about our first derivative, our second derivative. Those are the things that are going to really, really help us. So the first thing I'm going to do is I'm going to factor f of x equals, I'm going to factor this, x cubed minus 12x squared plus 48x minus 64. Again, I would do the synthetic division deal. But we know that this factor of x is going to give us a 0, right? So we've got a root at 0. And then when I do the synthetic division, plus or minus 1, 2, 4, 8, 16, yada, 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 all over plus or minus 1. I ran out of room there. You're going to find that 4 is a 0 or a root or a solution with a multiplicity of 3. So that's something that you will need to be able to do on your own, is going back and figuring out that synthetic division piece so that you can find the zeros. Now we're going to take our first derivative. So our x-intercepts, we're going to have x-intercepts at 0, 0 and 4, 0. That 0, 0 is also a y-intercept. Okay, so we've got intercepts at 0, 0 and 4, 0. Our first derivative is going to help us determine our increasing and decreasing intervals. So I'm going to take that first derivative, 4x cubed minus 36x squared plus 96x minus 64. I'm going to factor it, and I get 4 times x cubed minus 9x squared plus 24x minus 16. Once again, I would do some synthetic division here, and I would find that my x values are 1 and 4. There's a multiplicity involved there. I think I need to make this a little bit longer and a little bit straighter because it was kind of bugging me. There, it's much nicer. So now we're going to test our intervals for positivity or negativity to find out if we're increasing or decreasing in each interval by picking a value in that interval and plugging it into the first derivative. So a number between negative infinity and 1 would be 0. When I put a 0 in, I get, and I'm looking at this form right here, when I put a 0 in, I would get a positive 4 times a negative 16, which is negative. So this interval is one of decreasing. Then I'm going to put maybe a 2 in. When I put a 2 in, I'm going to get an 8 minus a 36 plus a 48 minus a 16. Let's see, negative 8 and 36 is not quite 48, it's negative 44, so that's going to be a positive. So that's increasing. We're really testing the arithmetic here. Then I'm going to put a 10 in. When I put a 10 in, I get 100,000 minus 9,000, right? 10 times 10 is 100. Nope. 900. So 10 times 10 times 10 is 1,000 minus 900. And then we would have a positive number, 240. There's no way. This is, 100, 240. No way. That's positive. So that's interesting because we have two increasings right next to each other. Didn't we say something interesting was happening? Said something interesting was happening. first of all, we have 4 multiplicity of 3, and then we had some pretty interesting stuff there with that multiplicity. But let's move on. We'll look at the graph together. I don't want you to get too anxious because this is exciting stuff. So our second derivative, love that second derivative, especially on a polynomial function. I'm going to look at this form of the first derivative, and I'm going to find that the second derivative is 12x squared minus 72x plus 96. Well, that's going to factor to be 12 times the quantity x squared minus 6x plus 8, which factors to be x minus 2 and x plus, x minus 4. So on a number line, this one is not as nice as the last one. So what am I going to do? I'm going to make it just as nice because that's going to bug me. So we've got 2 and we've got 4. We're going to test the intervals into the second derivative now because we're doing the second derivative test. If I put a 0 in, which lies between negative infinity and 2, I'm going to get a positive output. So that is concave up. If I put a 3 in, I'm going to end up with a negative output in the second derivative. So that's concave down. And then if I put, say, a 10 in, I'm going to get a positive output. That's going to be concave up. So we've got our concavity. We've got our increasing and decreasing. We've got our input. This is our input. So f of 1 is going to equal a decreasing to increasing would be a min. Increasing to decreasing, increasing to increasing, not a min, not happening. So we have a minimum at f of 1, or of f of 1. At x equals 1, we have a minimum y value. Now let's look at our concavity. So we've got some points of inflection. So we've got a point of inflection when x is equal to 2. So my point of inflection, f of 2, this is going to be tough. So I'm going to put a 2 in, and I'm going to do some synthetic division here. And I'm going to show you something that you probably already know. I'm sure you already know. Is that negative 8? Yeah, negative 16. So when I put a 2 into the function, I get negative 16 out. So f of 2, negative 16. And let's see, f of 4, so we take down that 1, that's a 4, negative 8, that's negative 32. That would be 16, that's 64, that's 0, 0, 0. That's cool. F of 4 is equal to 0, so you put a 4 in, you get a 0 out. I like it, I like it. So we've got a point of inflection at 2 comma negative 16 and 4 comma 0. We've got a minimum. We're going to have to put a 1 in. When we put a 1 in, I could probably put a 1 into the original function, not have to use synthetic division. When we put a 1 in, we get 1 minus 12 plus 48 minus 64. So negative 11, that's going to be 37. 37 from 64 is negative 27. Okay, if you want all of this work, you're going to have to hit rewind. So we have a relative, maybe it's a relative, or maybe it's an absolute. What's happening on the ends of these? Well, it's a 4th degree, so the ends are doing the same thing, and it's a positive leading coefficient, so the left is rising and the right is rising, so that means that this is an absolute min. We have an absolute minimum at 1 comma, I believe that was negative 27. Now we're ready to draw this graph, and it is a winner. Winner, winner, chicken dinner. Winner, winner, chicken dinner. Easy peasy, lemon squeezy. Okay, that's about enough for the rhymes because I don't know any other rhymes. Okay, so let's graph. We had, in our original function, we had x-intercept at 0, 0, and then 1, 2, 3, 4. So I'm going to go by ones along my x-axis, but my y-axis is going to be a different story because there's no way. The last time you saw with the positive 32, it didn't feel comfortable, making that point of inflection work. So not going to do that here. Our left end rises. So the left end rises, right? And it's going to come through here. And we're concave up. So we're concave up. So concave up is like this, right? So did you see how I drew that? I didn't draw it like this coming down. I drew it, let me show you. I'll do it again. I drew it concave up like that. Okay? So then it's going to go through that x-axis, and we had an important point here, an absolute min at 1, negative 27. So I'm going to call this 1, negative 27. Okay? So it's going to hit that min, and then it's going to, what's going to happen? We've got decreasing from negative infinity to 1, and then from 1 to 4 it's going to increase. So this absolute min is a turning point, so it's going to increase. And how far is it going to increase? Well, it's not going to go through the x-axis because I only have two x-intercepts, 0, 0, and 4, 0. So it's going to turn like this, but I don't know what's going to happen there. So let's see what else is happening. We've got a point of inflection at 2, negative 16. 2, negative 16, let's pretend that would be right about there. 2, negative 16. That's a point of inflection. There's also another point of inflection at 4, 0. So concave up from negative infinity to 2. We were concave up. Then from 2 to 4, we're concave down. So at this point right here, this is cool stuff right here, our concavity changes. See, so we're not drawing up like this anymore. Now we're drawing down because it's concave down. And then what's happening at 4? Remember I said 4 was a multiplicity of 3. 4 was a multiplicity of 3. A multiplicity of 3 is going to look like a cubic function going through the axis. And what's happening at 4? At 4, 0, we're concave up again. So now I'm going to turn and we're going to go concave up. That is a thing of beauty, other than the fact that I was a little excessive when I went concave up there. Yeah, we don't want to be too, because we don't want to curve back around, right? So we want it to look pretty, but we want it to also be accurate. So that's why when students go like this, when they're graphing, a polynomial function, I'm like, no, it doesn't just turn. And this is why, because of this right here, because of this second derivative. If you only knew that in Algebra 2 when you were graphing these things, you wouldn't just like do something like that, because it doesn't do that. A parabola completely concave up, right? Or concave down. A cubic function, there you go, look. Concave down, point of inflection, concave up. It's pretty neato, pretty neat stuff. So that was another example of a polynomial function that was kind of unique in a way where I'm not sure that we would have gotten, let me highlight it for you, not sure that we would have gotten the specifics of this part right here without the calculus or a graphing calculator. And who needs a graphing calculator when you know calculus? Okay, in the next video, we'll do a rational function.